I had to rejig this talk a little bit because of all the announcements. So we're going to discover what I wrote about together, which will be exciting. It was done this morning. So first of all, it's always worth, could you turn out the feedback, but always worth just introducing us in case of people don't know who we are, unless you're in the financial industry, then you may not have heard of us. We're a hedge fund, pure and simple. We've been around a long time for hedge funds, founded in 1990. Currently manage, the asset manager managed 27 billion under management. And we have about 1,500 employees and offices around the world. I'm just going to sort of give a little bit of history here about what we were trying to do and why we have some rather peculiar requirements that I realize are not standard for most people. So late in 2015, we started this team. And the situation was we have, obviously some number of batch farms, and they're all somewhat a little bit idiosyncratic. They were tuned for different things. Excuse me, these things were sort of bursting at the seams. We needed to grow these. We needed to essentially burst them into either buy a lot more data center or burst them into a public cloud environment. And the second aspect was we obviously were getting to the point where we really needed a new general purpose service scheduler, right? So that was essentially the ask, is a general purpose compute platform for both the cloud and on-premise. So when we broke that down to a series of requirements, it sort of came out like this. First of all, simplicity, right? We're a very, very small platform engineering team. The team that built this, well, he's sitting over here somewhere, right? It was, it was a few of us that built this environment. So simplicity was absolutely key. And there are other reasons, and we'll talk about why we really sort of focused on that. Second, as sort of trailed, we had a particular need for scale and speed, and I'll talk a little bit about why we have that. Thirdly, so I thought we wanted the ability to burst completely transparently into a public cloud when needed. We wanted to maximize the efficiency of the compute environment we already have. We have data centers of our own and things, and we wanted to squeeze as much as we could out of that, and then optionally burst into the cloud. And the last one, which comes last purely because I'm not going to say anything more about it, is security. What you will notice here in the requirements is not a huge list of extra features, right? So I'm not sort of been saying, oh, it must have a Spark thing, or it must have a this, that, and the other, and a this, that, and the other. Really, we're focused on the quality of that core scheduling platform first and foremost. Now, when we're looking at this, obviously at some level, somehow containers were going to play into this. We wanted something that was portable and was, transportable. A developer could build it and run it here, there, and anywhere. And sort of 2015, this was, excuse me, I think the state of the container market, if you see what I mean. But pretty much everything other than that was up for grabs. So let's go through those requirements a little bit and talk about them in the context of our decision. So, like I said, about late 2015, I think this was the sort of state of play of the schedulers that are available out there. Those are sort of the core three that we'll largely use. I'm sure there are others as well, but those are the three that we're really looking at. And then there was any number of sort of derivatives of these offered by numerous vendors. And pretty much all of them, when you sort of go and talk to these guys, it was sort of, well, it's really easy. You just push a button and you deploy this thing into your cloud and, great, right? And it's my ties on the beach from there in. That immediately raises a lot of red flags in my mind. Been there, done that in sort of complex enterprise environments. And usually these sort of, well, you just push a button and it goes kind of thing, it all falls apart. They're very opinionated sort of setups usually. And they hide a massive complexity. That button kicks off 15,000 bash scripts and God knows what, and Chef and all the rest of it, and it stands up lots and lots of different services, and they all sort of mesh together, hopefully. That works fine if you do it exactly that way. It tends to break in most sort of company environments where Maybe you don't have access to the internet. Maybe you're not able to run, DHCP or something. All kinds of stuff, right? It all tends to sort of fall over a bit horribly. Usually don't scale, not to the scales that we needed. They're usually designed for sort of smaller, POC size in our case, deployments. And that's fine, the button's great until the button stops working, and then you're in a world of PERT trying to work out what's going on, and it gets messy very quickly, and all that complexity really drives it. What you end up with is an engineering team who are shoveling coal frantically to either cope with the idiosyncrasies of your environment, the scaling issues, or just keep the thing running, right, because of the various problems that you're hitting. So there's a famous quote, I won't read it out. But there's another quote which I kind of prefer, which was by the guy who taught me infrastructure. That says, as quite rightly told me in a bar, if you can't explain your architecture on a bar napkin, you're doing something wrong. So that was the state of play. And then around almost exactly this time, this news story popped up, and sort of that was it. And was a reader. That was pretty interesting stuff. And then took that binary that was made available, I think it was like version 1 or version 2, I can't remember, it was very early, it was 1 or 2 weeks after that news story. Just took the binary straight from the website, no massive bash scripts and chef scripts and stuff to get it up and running. Looking, the docs were pretty limited at that point, so it was mostly sort of digging around in the code. And a few hours, and within that time period, a couple of hours, it was like literally, I think it was like a couple of episodes of Game of Thrones or something. We had 100 nodes up and running in a few hundred actually in Amazon, doing sort of real workloads, not production workloads, but realistic workloads, probably a better way of saying it. And the most important thing is we had a solid understanding of how it worked. Right? It was not opaque to us. There wasn't a massive config files off in a dark corner somewhere that we were sort of splunking around. We wrote the config files. It was, I don't know, 30 lines, 40 lines, something like that. And it all worked. So we had a pretty good warm fuzzy at that point, right? We know how this thing works at some level. Second one, speed and scale. So there are two real main driving workloads around our need for speed and need for scale. The first one is model backtests. This is, you have especially a quantitative model, you have a financial model. It needs to be updated regularly, changes in conditions of the market, new data from the market, whatever. Right? And then usually you want to run a certain amount of backtest, and you're going to run this thing over some number of years to sort of evaluate its performance and things like that. That's a lot of compute, right? The second one is research workloads. This is when, sort of, especially, again, quantitative kind of a researcher comes in. They have an idea, they have something they want to test out. They, maybe do some small testing on their own, sort of little tests locally on their box maybe. But to really actually evaluate the merit of their idea, they have to, again, run it over a significant amount of data, even over a lot of time or a lot of, sort of, a lot of the early access, a lot of assets. Or both. And what really drives the productivity of those is the speed at which you can do compute. So for models, it's how quickly can you get that updated model back into the market, right? That's absolutely key. And for the researcher, why the speed drives the productivity of the actual researcher, if they can essentially only run one test per day, you pretty much limited them to one idea or one test per day. That is a fundamental rate at which the rate at which they can move. Excuse me. So all these problems kind of break down into one thing, which is you got a fixed amount of compute to do. How quickly can you get that compute done? Right? So typical use case might be 200,000 core hours. If the choice is we'll do the 200,000 core hours in 1 hour or 20,000 cores overnight, that's a pretty clear choice. Right? So just to actually make that graphical, the first option here, there's not a pointer on this as I know. The first option here at the bottom there, that would be running it all night. And then the second one is burst a lot wider, run it an hour. And of course what you see now is you're dominated by how quickly you can ramp that thing up, right? The slope of that curve going up to the full capacity is actually a significant fraction of the volume underneath that, sorry, the area, yay physics, underneath that curve. So we did a bunch of testing on this, and Nomad just blew it out the water. That we were able to get to that maximum capacity in seconds as opposed to minutes or even hours. So we were scheduling, I think, 2,500 containers per second. And sustained, that's not just, we just did it once and said, yay. We actually ran that all day at that rate, and it just sort of kept on going. Third, bursting. So I think when we're talking about this, it's worth talking about how we think about our public cloud and versus on-prem kind of strategy, how we actually sort of what our mental model is for that. So first and foremost, we want to make best use of those invested resources we already have, right? We have data centers, computers we've bought and invested. We want to use those first and foremost. We want to have the option to then burst those workloads to a public cloud provider, any public cloud provider potentially. And that operation should really be low touch, if ideally automatic. All right, you shouldn't need to re-architect your application because you're going to have to move it to the cloud, or your deployment because you have to move it to a public cloud. That's not really what we're trying to achieve here. So the immediate question should be, well, that means that you're essentially, in your cloud provider, you're limiting yourself to the lowest common denominator, right? If I go and look at Amazon's service list, I think this was a snapshot as of a couple of days ago. God knows what it's like now. Yeah, there's a ton of stuff here, right? And that's part of the appeal of the public clouds, right? I can go there and I can get, there's all this machine learning stuff. I don't know where it is, lost it. Anyway, it doesn't matter. Analytics, a bunch of stuff which developers just love, right? It's great. Does that mean you can't leverage that? Well, we take this sort of strategy that fungible things should be fungible, right? Should be fungible. A computer is a computer is a computer. Deploying code is deploying code. It's kind of mundane. It's boring, right? I shouldn't be necessarily building that sort of really low value stuff into as a gate into my doing potentially more interesting things. And application specializations are special. Right? So if you are a developer, you're an application team, and you choose to use, I'm plucking something totally out of thin air like BigQuery or CloudML or something. Okay, fine. That is a specialization of your application. You're in control of that. But what we shouldn't be doing is blocking the path to the cloud based on things like deployment and running and job submission and monitoring and logging and all that kind of stuff, right? So we're looking at essentially a hybrid or burstable cloud thing. And if you ever try to do a Google search for any of these, it's pretty awful. You end up with lots of pictures like this, people in shirts in very oppressive lighting environments. I don't know what these guys do, but I don't think they're an engineering team. This is there's a lot of solutions out there. There's a lot of companies that will sort of sell you a solution, but they're somewhat heavy and expensive, slow, usually quite complex, and a big lift to sort of get yourself into a hybrid environment. Climate 4, efficiency. So let's talk about this in sort of two axes. First off is probably pretty familiar to most people here is workload types. Most organizations have many different, have at least two different types of workloads. They have long-running services. These things are running APIs and people hit them and they do stuff. And then they have, some amount of batch workloads, right? Where they're coming in, they're doing data processing and, putting down results at the end of every day or something like this, right? And for us, we're the same. We have exactly this. In our daytime, trading hours and things like that, we'll have, a lot more services up and running, doing the trading and things like this. They tend to be more predictable, right? They, going to be up during trading hours, for example. And their capacity demands will obviously, do things like follow, market volatility or whatever it is, or volume. And then we have the batch type workloads, which certainly don't always fit on premise. and are very variable and very unpredictable because they're these things like model runs or research runs or things like that. There's no way to predict them, right? And they can run at any time, right? So we end up with sort of, this sort of little graphic here of, what a capacity might look like during the day versus, overnight. And ideally, we want to co-locate these workloads, right? So we can sort of swing the capacity either way. There's another aspect of efficiency. Most enterprises have some amount of unused capacity, right? Whether it's whole DR sites. Some enterprises do this where they have complete sites which are doing very little until there's a DR incident, or they have staged expansion, or they have burst capacity for other systems, right? So, they're going to right-size their traditional environment for, whatever it is, the maximum compute that it needs to do, right? So the other question is, for us, could we leverage some of that underused capacity? So if it was a DR capacity, this might be sort of normal, right? Can we actually sort of interject ourselves in here dynamically and to leverage that underused capacity? So obviously Nomad was the answer to this, although that's why I'm here. Let's sort of go into how we actually built this a little bit. So this is a sort of cartoon of our sort of macro architecture. We have multiple Citadel data centers. Our data centers are a bit further spread apart, so we tend to treat them as Nomad regions, and each data center is its own region. We have multiple cloud regions, I should say, and we spread out our Nomad and Comsol servers in those availability zones, obviously. And then, of course, because the meshing aspect of Comsol and Nomad, we have to put a VPN sort of tunnel between these two regions to allow the servers to talk to each other. So let's talk a little bit about that's the sort of big picture of how it looks. Let's talk about the actual capacity we provide to those servers. So we sort of break up our capacity in all places into two tiers, right? We have our dedicated tier. That means that that's Nomads and always going to be Nomads, and you'll always have it. And then there's the ephemeral tier, which is this best effort. You're going to get interrupted at some point kind of capacity, right? So in the cloud, that's really easy. That's in Amazon, it's Spot, and in Google, it's what they call preemptive VMs. And the sort of basic premise of both of these are the same. If you don't know what they are, is that the cloud providers auction off or discount underused capacity, and you can use that capacity until they need it for someone else or a higher paying customer, and you can, you'll get preempted and moved off. So we actually heavily use this for a lot of our compute. The reason being is you can get up to about an 80% discount, and especially when you're running a lot of data processing workloads, that makes a big difference. So you have to have a bid strategy. This actually shows the market value of a particular instance type, which I've now forgotten and hopefully didn't put on there. Doesn't matter. And you have to have a bid strategy that you put in there, and there's a ton of work to work out what the optimal way of doing that is. But that's another talk. So we have these two classes of compute, both on-premise and in the cloud. On-premise, the ephemeral compute is that DR capacity, right? If there's an event or something else needs it, we take that away from Nomad, and thanks. And the on-prem, we have the spots, and we have the dedicated, which are just machines dedicated to Nomad. And the way this sort of is exposed to the users is we tag all the machines with essentially their class. And you can actually, in your job spec, select what class of machine you want to run on, right? So if you're just running a batch job, and okay, if it gets preempted, okay, it's annoying, but it's not the end of the world. You would choose that ephemeral class, and you can get a discount for that. But if you're running sort of long list service and you want it to be there forever and you want to have minimal interruptions, then you choose the dedicated tier. This is pretty basic stuff, so I'll just run through it real quickly. This is a traditional sort of application might look like in a traditional environment, anyone's traditional environment. You have some service foo that's dependent on bar, and it goes through a bunch of load balancers or F5s, and how this works, it hits the database or something in the end. What happens to this when you put it in a Nomad cluster? That load balancer in the middle goes away and is replaced by Console for all its service discovery and for a good part, most of its load balancing. Front ends, we actually use Fabio. Similarly, we use Console for routing the front ends into the actual cluster. So Console provides all our internal load balancing, our internal service discovery, and actual fact, because all our customers are internal, we can actually use it for our actual location of, from the desktops, if you like, into services running. Fabio we use as the the interface between our Nomad clusters and the outside world. And all this works absolutely fantastically within a region. It's easy. It gets a little bit more complicated when you're doing multi-region. If you've got a user here who's hitting a service foo, that's pretty easy if you just sort of hit one in one region and hits a service bar. What happens when that bar service goes away and we've got a route to the bar service running in the other region, right? This is pretty much a work in progress for us, but whoops, didn't know what happened to that. No, we're sort of still working on this actually, to be honest, but with prepared queries and things like this, you can actually sort of route the traffic across the regions in the case of a failure of a particular service. Logging monitoring, I don't know if you saw the PagerDuty talk. It was quite a nice talk. We have a very similar sort of strategy around our logging monitoring. We actually expose up a statsd daemon into every container running on a host. So this is actually a little cartoon of a single compute node with two apps running on it. We expose up a statsd daemon that provides the sort of application level monitoring for our customers. We expose up an our syslog port. We also use the Docker logging drivers to capture standard error and standard out and send it off to a Splunk platform. This all works fine. It all tends to get a little bit troublesome when you're doing these extremely large runs with 100,000 containers or something like this. It tends to blow out a lot of logging infrastructure. So what we do when we're running these things, these 100,000 node jobs or whatever, 100,000 container jobs, you don't need to log and monitor every single one. So we have the ability for users to sort of dial back probabilistic logging. It's sort of a pseudocode here kind of thing, how that might work. And they just specify what fraction of their actual jobs they need logged and monitored. So 10%, 1%, something like this. Alrighty. User APIs. This is the bit that got heavily gutted this morning. So all the missing bits. So there are some stuff that we as an enterprise and most places over a couple of guys' shops need. We need authentication and authorization. We don't want Bob to be able to kill Jane's jobs and vice versa, right? Either accidentally or on purpose, right? So we also need some amount of tenancy or quotaing. And actually really important for us was policies. And I'll sort of dig into a little bit about why that was. And by policies, I mean, don't let the users do this thing, right? Always make sure they have this thing in their job spec, that kind of stuff. And of course, capacity management. Unfortunately, or fortunately, all three of these have now been pretty much superseded by the announcements yesterday of Console ACLs, namespaces, and Sentinel. But I think it's worth just sort of digging into a little bit about how we sort of solve this, because we actually do use it for some other stuff as well. So we actually wrap the APIs of Nomad, which allows us to inject our own authentication system, which is an internal thing. Doesn't work like this. Where they actually call Nomad API. They use the Nomad API, but we actually sort of supplement that a little bit. And our job API essentially intercepts that and passes on the actual API call into Nomad after it's done appropriate authentication. It also does a lot of the capacity management. These API set does a lot of capacity management, so we actually extend the Nomad API so the users can actually sort of scale the underlying capacity in their tenancy if needed. Policies. This was quite a big deal for us. If you've run Docker in a production environment, there's some pretty sort of scary security things you have to be aware of. So we heavily lock down the use of Docker. It's not like you can specify any Docker parameters or anything like that. It's very tightly locked down this way and other ways. We make sure that all the people are logging their stuff in the right way. We sort of essentially interject that logging stanza. We have a call out to our essentially what's like a CMDB, I guess, that just checks the application that you're running. One, that you're actually allowed to run that application. That service is, part of your tenancy, if you like. And secondly, if, for example, you're saying, okay, I need this thing to run in the cloud, is it actually approved to go to the cloud? Is this something we want in the cloud? Yes or no? So these are the kind of sort of policies that we put in place and we enforce actually in our APIs, which I guess now we'll enforce in Sentinel. So what does that look like from a user experience, especially that model researcher we talked about? So on the right-hand side here is a sort of example job spec, that you might be, that they might be working with. And they generally develop this either locally or on the desktop or sort of on site. And then they'll run some small workloads on our, on-prem clusters. So they specify a region, Citadel, it's batch type and maybe a data center A and, maybe just 100 containers, no big deal. Then they get ready to scale up. Well, essentially all they do is just change some parameters in their job and resubmit it. And now they're scaling into a public cloud, right? Across potentially multiple data centers, up to 10,000 nodes. And of course, moving to a different region, if that region develops a problem, is pretty straightforward. You just change the region in the job spec, and it all gets forwarded off and spins it up in the new region. So there's one last slide I sort of injected at the end here, after talking to people about some other operational aspects of how it's been going for us, basically. And just sort of on a personal note, I actually did a talk years ago now about upgrading OpenStack clusters. And I think the title was Hours of Boredom Punctuated by Moments of Extreme Terror. That was literally the title. It really was. I mean, I had a bunch of Ansible scripts and, sort of click through the OpenStack cluster and, very complex to upgrade this thing from one release to another. And it went fine until it didn't, and then, you lost a lot of sleep. Our upgrades for Nomad console have been entirely painless, I think. For the most part, we just sort of, everything is deployed on, on-prem with Ansible. Actually, into our AMIs, we use Ansible and Packer as well. We just change the version. It just pulls down the version and goes through the servers and replaces binary and restarts them 1, 2, 3, and then one by one, and then roll through the fleet, replacing all the agents. That's been very different experience. The upgrade of the OS and reboots, they have to be managed. Don't take down all your servers at once. Things will stop working. It's not magic. But generally painless, right? Some of the areas that are going to cause us problems in the future, not currently, but they're going to cause us problems, is preemption. We would like Nomad to have the ability to preempt workloads. I've got a high priority job coming in. I'm running out of capacity. I'm going to have to pull something of lower priority. And all the parts are there. It's just not quite in Nomad right now. So a bit of advice. Give Nomad plenty of CPU, the actual servers, CPU and memory. I think we run in our sort of Amazon regions, we run, I think, the M4 series. There's nothing particularly special about them, just sort of err on the side of bigger. Multi-region failover requires careful design. That's something we're still working on. It's certainly not automatic. Nomad is a region-aware scheduler, not a multi-region scheduler, if that makes sense. So if you've got a job running both sides and you lose one region, then okay, fine, you can have ways to route the traffic to the new side. But do you need to expand the capacity over there? I mean, how do you manage that? Or do you need to preempt jobs because you've got to make way for things that are only running in one region? There's a fair amount of careful design that has to go on there. By far, our largest pain point has actually just been Docker itself. And I think anyone who runs Docker at any kind of scale will know what, I see people nodding, talking about. The actual Nomad binary's been fine, but Docker, yeah. Summary. I would say never underestimate the importance of simplicity. It was after speed and scale, probably number one, right? Do you actually understand what the hell's going on in your infrastructure? Right? Nomad, we've been a user since I think 0.2 or 0.1, I don't quite remember. It's a couple of weeks after the announcement. Serious users since 0.4. It's in production in multiple Citadel data centers and multiple cloud regions. The good things, the things we love, the speed, the simplicity, able to scale, and our ability to integrate it. It's a very clean API. We've done a lot of integrations against our own systems. That's actually been fairly straightforward because of that sort of very well-structured API. The challenging bits, I was going to say, can you actually see those are striked out? I don't know if you can. Authentication, tenancy, and policy, which Caius now are no longer a problem. Preemption and DR strategy, that is still work that we have to do, and of course, the Docker thing. So that's it. Thanks.